came to Harper and studied ag engineering at MEng level. Joined Alex, born and brought up on a Herefordshire cider farm. Came to Harper and studied ag engineering at MEng level. Joined JCB as a graduate engineer. First of all, he was working on research on the load-all lines, and then subsequently on the tractor interests. And ultimately, as far as the meeting is concerned, it culminated in the work as project manager on the world's fastest tractor. So I think that as a brief sort of resume of Alex's bio resume, then I'll hand over to Alex and let him get on with the talk.
Okay, thank you, Simon. Right, so we'll start off with a video.
Tractor.
Tractor's job, landwork cultivation, leading, tail rowing, de-stoning. As long as you call it digestate, poo spreading, muck spreading. Yeah, it's shit spreading, isn't it, really? That's what we all know, don't we?
Guy Martin.
I just want to go as fast as humanly possible on whatever I'm on. Whether it's a push bike, whether it's a car. I love going fast. I love it. Tuck, smack on the head, I know that. But I'm all right, I'm all right, no one's died. No one's died.
JCB.
They're amazing things, aren't they? Piece of kit, eh? Oh, it's JCB. They don't mess about, do they? They don't mess about. A trick, innit? They're doing it. They're doing it.
$150 miles an hour or something like that. That's a proper record. That is a proper record. Not easy done though.
Okay, there we go. So, as Simon said, my name's Alex Skittery, and I was lucky enough to be part of the world's fastest tractor project here at JCB, working as the project manager. So, really, I've got about half an hour, 45 minutes, but Simon, if I go on for too long, just tell me to stop, and then we can do questions. But there's lots of really interesting stuff that I want to share with you guys and girls today. So first of all, I'll talk a little bit about why we did it. You know, what was the point in it all? Then I'll go through the challenge, what we did, and then we'll look at the results. So after that, as Simon said, we'll open up to questions. So please do ask loads of questions, and I'll do my best to remember all the details. So why did we do it? Well, really the main reason was Lord Bamford wanted to do it. You know, he's the main man. He owns the company. He's really, really passionate about the fast track, and you know, he said, right, we've got to do this. Fast is in the name. You know, I want to have the fastest tractor in the world. So that was kind of the challenge set, really. And you know, JCB aren't a stranger to doing these world records. In the past, you know, we've got the world's fastest backhoe. So that's on the top right there. So, you know, 96 miles an hour. That one actually does wheelies and flames come out the exhaust. So a fair thing, that is. And then obviously the Diesel Max car, so 350 miles per hour, and coincidentally pushed by a fast track as well. So, you know, a good sort of taste back then of things to come. So really, you know, in terms of a company, why did JCB as a company want to do it? Well, you know, we're really, really passionate about innovation and engineering at JCB. You know, every product that we try and produce, we try and get it as innovative as possible, and really just try and push some of those boundaries. I think this project was seen as a way of doing that. It was a little bit different, but it just showed what kind of new technology is out there and can be applied to machines. And I'll cover some of that a bit later on in the presentation. You know, it was all about teamwork, and it was a really young team that worked on this. It was made up of a few graduates, a few apprentices. So there was 6 full-time engineers on the project. I think our average age was about 27. And then, you know, do the median, and it was about 23. So a really young team. Obviously, we had quite a bit of help from some of the more experienced guys. You know, some of the people that had been working on fast tracks for their whole careers. Some of which are most likely listening to this now. So thank you to all of you guys. It was all about delivery as well. You know, at JCB, it's pretty fast paced. There's a lot going on. You know, you've got a job to do. There's projects happening, and really this was exactly the same. We had an objective set by Lord Bamford. We had an end date, which is when the TV program wanted to be aired, and then we just had to make it in between. There was no shifting on that. I think we had about 9 months to do it. At the end of that, we had Lord Bamford watching. We had all the TV cameras. So, you know, no pressure, but it had to work when those people were watching. And then, of course, fun. You know, if you can't really have fun at work, you need to try and find something else to do, because you spend a lot of time at work. You know, I'm here now, so you've got to enjoy it. But really, a key thing was we had to do it safely. So all very well having fun, but it had to be done properly. So we adhered to all the different JCB policies, health and safety, all the different design policies, FMEAs, standards. You know, it was done properly. So that's a bit on the background. And now let's talk about the challenge. So in front of you, you can see our 4220 fast track. So, you know, this is what we had to work with. It's a heavy lump, you know, 8.5 tons when you've got front linkage on, the rear linkage. Aerodynamically, you know, it wasn't designed with aerodynamics in mind. You know, it doesn't need to be. It doesn't go fast enough for them to have a big effect on the vehicle. So a key thing that you've got to get right when you're going fast is aerodynamics. And there's this magic ratio that the CDA, so that's the coefficient of drag times by the frontal area. And when you measure it on the tractor that you can see in front of you, it's about 6 meters squared, that frontal area. So it's quite a big sail flying through the air. The coefficient of drag is a little bit harder to determine, and we actually did that by performing some coast down testing, which came out at about 0.58. So multiply those together, you get about 3.5. Power, you know, it's about 240 horsepower gross. So, you know, plenty of horsepower to do what it needs to do in the field and on the road, but you know, we needed a bit more really. So max speed, it is the fastest tractor, production tractor you can buy, 43 miles per hour. But of course we wanted to go quicker than that. You know, there'd been quite a few record attempts in the past, and we thought we could do a lot better. You know, we thought we could go a hell of a lot quicker than some of these other attempts. But really a key thing for us that differentiated us from those different record attempts was that we wanted it to be as close to a tractor as we could get it. So all that, you know, that fast track DNA, as many parts as possible, we made sure we used on the tractor. So we actually got the CAD model of the 4220, opened it up, and just started modifying bits that we needed to actually produce the tractor that we made, the world record tractor. So actually, when you look down the parts count, about 50% of the bits are still from a standard fast track. So a bit more about the target. So we knew what we were starting with, the 4220. We knew some of those key attributes, and then we needed to work out how to make it go quicker. So Lord Bamford said, right, you can do it, you can spend some money and some time, but I want you to go 150 miles an hour. Go away and work out how you can do that. So first thing we had to do was work out, well, you know, what are the constraints? And really the key part of that was, where are we going to do this record? And, you know, we looked all over the world. We looked at different runways here, there, and everywhere in America, in Spain. But actually, we sort of came full circle and said, well, it'd be quite nice to do it on home turf. And we actually settled on Elvington Runway, which is up near York. It's an old RAF base. You can hire the whole place out and just, you know, use it for whatever you want to do. So there's loads of different speed records that are done at Elvington. So that was one of the key constraints. We knew we had 3.2 kilometers to get the job done. And looking into the record, it was for the world's fastest tractor. And one of the stipulations of this record was you had to do it in both directions. So you'd start at the one end, do your top speed run, and they'd measure the average speed that the tractor would be going in the middle kilometer. Then at the end, you had an hour to turn the tractor around and then zoom back down the other way. And then they would average that flying kilometer speed to give you your world record speed. So that was really important because, you know, the defined length of the runway meant we had to accelerate this tractor up to speed and be able to stop safely and do it in the other direction. So we knew the length, then we looked at the vehicle. So, you know, taking the thing back to first principles and all that good maths behind it, you know, we came up with a few key attributes that we just had to get right in order to achieve our record speed. So those were the weight of the vehicle, the power, the CDA, gear ratios, things like rolling resistance in there as well. So all these things, and rather than writing the sums out and trying all different combinations, we actually created a simulation model where we could quite easily change the different attributes and just sort of perform all these different iterations until we came up with sort of the main targets, and we set these right at the beginning of the project, just so everyone knew exactly what they were aiming for and what they had to get done. So, you know, the target was 150 miles an hour, JCB fast track. So the model pretty much spat out these three key attributes. So weight, we had to try and get down to 5 tons. The CDA, we had to get to 2.4, and we needed at least 1,000 horsepower. If we hit those things, we had a fighting chance of actually achieving what we've got set to do. So the next bit of the presentation is taking you into a bit more of that detail on how we actually achieved this and all the engineering behind it. So we're going to sort of strip away all the bodywork. We're going to look at all the good stuff underneath the skin. So first thing we'll talk about is mass. We had to try and get 3.5 tons out of the tractor, and someone told me the other day that's basically a Range Rover and a Mini we had to remove from the machine. So a fair amount, really. So the first things we did were we removed some of the excess bits. You know, some of the parts of the tractor that we didn't need to achieve the record. So things like the front linkage, for example. Then we looked at all the parts and said, well, what could we make from aluminium? You know, what can we make lighter and optimize? And then really a key one where we did save a lot of weight was the chassis. So again, we started with the fast track chassis, and we actually we used some software, some topology optimization software, where we put in the different loads that we calculated that the chassis and the machine would be subjected to during the run. Pressed go, and then it basically produces a model like you can see there in sort of the top right. So this is the blue model you can see. I know I'm just looking at my screen. If people can't quite see all of that, there's a way you can actually minimize some of the zoom windows if you just sort of hover over them and press the hide thumbnail video. So if you're struggling to see, you can do that and you might see a bit more. So as you can see, that blue image there, it comes up with quite weird and wonderful shapes, which, unless you're doing a full casting, aren't really that useful in real life. So we then got that model, applied a bit of common sense and logic to it, and produced the model that you can see below, which we then put into FEA, or finite element analysis software, just to validate that, yeah, this chassis that we've produced is going to do the job. It's not going to bend when we're doing the record run. So so yeah, that's the chassis really. I think we saved probably, I don't know, maybe 350, 400 kilograms by performing that exercise on the chassis. So, you know, weight saving was a big thing. You know, every bit we were designing had a weight target against it, and we knew what we needed to achieve. So next was aerodynamics, and you know, normally we're not too worried about aerodynamics when we're designing our machines. You know, 40 miles an hour, they're only just starting to have a bit of an effect on the vehicle. But obviously for this, they were really, really important. So we actually worked with some of our friends at Williams Advanced Engineering, and they performed a lot of the CFD analysis for us, which is basically a virtual wind tunnel. You know, you blast virtual 150 mile an hour wind at the machine and look at and analyze where it goes and what it does. So we did many iterations of this CFD analysis to produce the tracks that you can see in front of you there. So key things that really improved the aerodynamics of the machine were, the first one, the easiest one, is the frontal area of the machine. So we actually lowered the whole thing down by 400 mil. I think it was about 200 mil on the axles, and then about 200 mil on the cab. We also then made the cab narrower by 300 mil. So that really reduced our frontal area down. I think we got it down to about 4.6, so about 1 meter squared we took off the frontal area of the machine. And then we got onto the slightly trickier stuff, which was the aerodynamics. So quite a lot of learning went on with this, and really the key thing I learned was it's just got to try and slip through the air as easily as possible. It's got to just try and not disturb the air that it's pushing through. So key things that we added to the machine were obviously the front bumper, or the front splitter, and really the main job of that was to guide air around the tires, but also guide it into the cooling packs, and I'll talk about those cooling packs in a bit more detail soon. We also put an under tray on it, so underneath the machine, just to stop air trying to escape up through into the chassis of the machine and increasing that coefficient of drag. We also put fins on the side of the cab just to try and get the air to not circulate around the back, but just keep on sliding straight past the side of the cab. So they did loads of CFD. They kept we kept having meetings with them and looking through PDF reports, and it was working, but it didn't really make much sense to us. So we looked at other ways that we can actually visualize this CFD. And the best thing that we did was put all the results into virtual reality. So this is where you wear your special glasses and you hold two wands in your hand, and you can actually walk through the machine in the virtual space. So you can see here all of the yellow lines on this is all your 150 mile an hour air hitting this machine. And really the key thing to do here is keep everything yellow. If it goes red, the air is speeding up. If it goes blue, the air is slowing down, which increases your coefficient of drag. So this wasn't our final iteration. I don't think this has got the front bumper on yet, and it's got a slightly different roof, but you can see it really helps to just visualize what all this CFD means. So yeah, a huge amount of work went into the aerodynamics of the machine to help it out. So you can see that you could get right down, look at even what the axles are doing and what effect that has on the air. So next, I'll talk about the driveline. So the engine producing all this power, and I'll talk about that in a minute, but we've got to somehow transfer all that power down to the ground. So obviously we had a clutch, we then coupled that to a transmission, and then that transferred power down through the axles to the ground. So we'll just look at those in a little bit more detail. So the first thing, the first step in the chain is the clutch. And I mean, we were asking a lot from a clutch. We had huge torque requirements. I mean, I think the engine produced about, at its peak, 2,300 Newton meters of torque. It's then got to be able to slip because the machine was geared so highly, so it could achieve those top speeds of 150 miles an hour. We actually had to slip the clutch when we were setting off for about 15 seconds before it was fully engaged, and we could actually start the run. So a huge amount of slipping. And also it had to be low inertia. I mean, we were bolting this to the crankshaft of our engine. You know, this JCB engine, which I'll talk about in a minute, you know, it's not really designed for hanging huge diameter weighty clutches off. And you know, the first clutch we looked at was a big clutch out of a lorry, you know, a single plate dry clutch. We did all the analysis and said, no, you know, spinning at 3,000 RPM, this is not, the crankshaft's just not going to last. That torsional resonance is going to be way too high. It's going to be wobbling all over the place, and it's going to be absolutely no good. So we looked sort of around JCB, you know, trying to use some of these parts out of our parts bin. And we actually decided on using our multi-plate wet clutch, which is fitted to quite a few of our tractors. Not the current production ones, but a lot of the 2,000 and 3,000 series fast tracks use this exact clutch here. And luckily we still had a few in the cupboard. So we dusted one of those off, and this absolutely ticked every single box that we had. It had a really high torque capacity, and that came from the 8 oil immersed clutch plates within that. And a key thing is here, it's a wet clutch, so that meant that you could slip it. You know, it loved being slipped. There's a lot of capacity there to slip it without the oil getting too warm. Another key thing was it was simply supported, so it had a bearing each end, and that meant that it didn't have such a high moment of inertia, and our crankshaft was a lot happier. The calc said, yeah, this one will definitely do the job. And then of course it's software controlled as well. So there's an electronic proportional valve on there, and we could play tunes with this till our hearts were content. You know, we could do things like, you know, basically we had a launch control mode, so we could just lift the foot. The driver could just lift his foot straight off the clutch. The software would limit and control that slip, and get the vehicle going. It also acted like sort of a fuse in the driveline. So if the torque got a bit too high, that valve could start to slip, just, you know, based on the pressure within it, and that could, you know, just help protect our driveline. So that was the clutch. We then coupled that to a nice and simple 6-speed manual gearbox, and a key reason for doing this was that it was just nice and light, you know, 200 kilograms. So, you know, weight saving was a huge part of this project. So we thought, well, we'll use a nice lightweight gearbox, nice and simple. And then we coupled that to a JCB fast track axle. So we did modify it a bit. We put some big diameter half shafts out of it from an 8000 series tractor. We locked up the differential so that we wouldn't get any wheel slip when we were setting off. And we also locked up the epicyclics in the hubs, just so that, you know, we had that gearing that we needed to achieve those top speeds. So really good. It didn't like turning really sharp corners, but luckily we didn't need to do too much of that. So we're pretty happy with the driveline. We thought, yep, I think this is going to do the job. That then needed to transfer that power down to the ground, and that was via the tyres. I think these were probably the thing that caused me the most sleepless nights on the project. You know, they had some fair requirements. They had to be safe and stable at 150 miles an hour. They still had to be a tractor tyre. You know, we didn't want to just fit an aircraft tyre to the machine like a few other people have done in the past, and especially to these speed liners that you see on the Bonneville salt flats. It was quite tempting, but they are quite heavy as well, these aircraft tyres. So we thought, no, we'll use a tractor tyre. And we went to BKT, who are a supplier of tyres to us, and we ended up using one of their Ride Max tyres, which we actually fit to quite a few of our tractors, especially in the more industrial applications. So they used exactly the same tyre mould, but they did change the compound of it. So we did quite a lot of work, and we actually added a bit more natural rubber to it, which then helps. It produces less heat and more grip. So quite a few sort of racing tyres use this sort of methodology in the compound. We then added 2 steel belts to the inner surface of the tyres, and what these did was they helped it to not grow at speed. On the rig, you can see the video looping on now. We can actually measure that growth, and even with these steel belts, when that tyre was spinning at 150 miles an hour, I think it probably, from memory, the measurement was about 20 mil growth in diameter. So they were doing a pretty good job, these steel belts, to try and stop these tyres from basically pulling themselves apart. We also shaved the tread blocks down a bit, from about 25 mil down to about 10 mil. And that just helped with the lateral stability of the tyre, and it helped reduce rolling resistance as well. I think by doing that, we went from about 3% down to about 2.5%. So a few changes to the tyre, same rim that we use today, and we actually did a load of FEA analysis first to try and work out, you know, what we needed to do to this tyre. So did all that, but really you can't really beat doing a good old rig test. So got on a plane, went to Germany and found this rig here. It's the only one we could find. We looked for a long time. I think there's one other place in America in a military base that could test a tire to this diameter to the speed that we were at. So we managed to find that, and what we did was we simulated the run that we were going to perform. So, you know, starting off slowly, going at top speed for a short while, and then decelerating. So, you know, measured temperatures, tire growth, air pressures. So we had a good set of data there. And then we thought, well, we need to know what the sealing conditions of this tire are. You know, what are its limits? So we pretty much ran it until destruction, and it created quite a big bang when it went off. I think it actually shook the test cell we were in. But you know, it was really important to do this because it sort of gave us the maximum temperatures that the tire could cope with, gave us the maximum air pressures inside, but it also told us the failure mode of the tire. And what we found was that it started excessively vibrating before it went bang. So this gave us a bit of confidence then, because we thought, well, now we can actually fit some sensors to the vehicle. And we actually ended up fitting tire temperature sensors, which live monitored the temperature of that tread when the vehicle was going along, remote air pressure sensors as well, and also vibration sensors fitted to each axle. So we inputted all this data in, and we worked out what the limits were. I think it was about 60 degrees we settled on for the inside temperature of these tires before we would have to stop the run because they were getting too warm. And we fed all that into our ECU, and it then alerted the driver. If any of these sealing conditions were reached or getting close to being reached, it would flash a big red light on the dash and say stop. So it just gave us a little bit of confidence that these tires weren't going to go bang when we were running. So engine. So Lord Bamford said, right, you can do the project, but you've got to use a JCB engine, which is fair enough. So we used the JCB 672. So this is a diesel engine. It's got 6 cylinders and a capacity of 7.2 litres, fitted to quite a few of our excavators. And just like the tractor, we tried to keep as much of it common as we could. So we ended up with a common, or we didn't change the block, the cylinder head, the pistons, the crank, the rockers and the rocker shaft, water pump, oil pump, fuel lines, kept all of that exactly the same, and then pretty much just bolted stuff on the outside of it to increase its power. And you know, how do you get more power? You need more fuel and more air, and that gives you more power, and also quite a lot more heat. So we'll go now through how we achieved that. So more fuel, that's the first thing we tackled. So we used the common rail fuel system that the engine had. So this is a Delphi system, same ECU that we fit on our stage 5 engines, but we did have to modify the software quite heavily so that the fuel maps could cope with this extra fueling. We fitted a huge fuel pump off, I think it was like a 15-litre engine out of a train. We also then used injectors off that same engine, which, I mean, they ran at, the rail pressure was about 2,500 bar, and the flow rate of these injectors was about 2.7 litres per minute. So, you know, big old things capable of stuffing plenty of fuel into those cylinders. And I think actually, even though they were running at quite a high flow rate, we still achieved about 5 miles per gallon when we were running at top speed. So not too bad really. I think my old Land Rover does a similar amount at about 50 miles an hour. So when you sort of convert that back, that's about 200 litres of fuel per hour. If you compare that to, you know, a tractor today, probably ploughing, it might be doing about 35 litres per hour. So just gives you a comparison of what kind of fuel it was using. So we've got loads of fuel now. We need loads of air to combust that fuel. So first thing is big turbo. So the green turbo is the turbo that we started with. The red turbo is the turbo that we fitted to the engine. So this was a big old lump. I mean, it was running at 5 bar and delivering about 1,000 litres of air per second into the engine. So really good, but the trouble with huge turbos is they take a long time to spin up. So you get a lot of turbo lag. And really that's because at you know, low engine speeds, you've got a lack of exhaust energy to accelerate that turbine up. Up to that speed. I think this ran at about 150,000 RPM. So in order to sort of fix that, that turbo lag, we looked at using an electric supercharger, which we did end up fitting to the machine. So these are being used a lot more in hybrid vehicles of today. We ran it at 24 volts and we powered that by a set of lithium-ion batteries. And that really was, you know, lithium ions are a lot lighter than traditional lead acids. So this was quite an impressive thing. It could get up to 50,000 RPM in less than a second. It really was instant boost. So this would kick in at sort of anything below 2,000 RPM, where there just wasn't enough exhaust energy to spin that big turbo up. And what this did was it pumped air directly into the compressor side of the turbo just to get it nice and spinning fast. And then we had pressure sensors which would then automatically turn it off when the turbo had got up to speed and it was actually breathing more air or sucking more air in than the compressor could deliver. So fitted that. Worked really well, but actually it still wasn't quite enough. We still, during the dyno and the vehicle testing, we still had a bit of a turbo lag issue. So we looked at a few other options and we thought, well, we could fit NOS or, you know, nitrous oxide, but it was a little bit boy racer. We thought we could probably do something a bit better than that. So we looked at a system where an air pulse system. So what this does is it injects 20 bar, so high pressure air into the exhaust manifold, and this then spun the turbine compressor to really just counteract that lag. So it gets it spinning nice and fast. And we used this quite a lot during initial set off of the vehicle, and also then during each gear change. And we were running this for about 5 seconds per gear change. So we actually held that air using a scuba diving tank, which is actually fitted to the back of the vehicle. And I think we would use about a scuba diving tank's worth of fuel, of air every run. So it really was giving it some air and really helped with that turbo lag. I think rally cars use it. I think some of the Volvo engines of today use it as well. So it is a system which is starting to become a bit more popular in engines of today. So we've got more air, we've got more fuel, and as I said before, that gives us more power, but it also gives us a lot more heat. And this is, after tyres, it was probably one of the hardest things to get right, the cooling system on this tractor. There was a fine balance between it being nice and warm so that it would start, but then getting that air, that that air going into the engine nice and cold, so it was nice and dense and made loads of power. And the reason I say it needed to be nice and warm to start was we actually lowered the compression ratio of the engine from about 20 to 1 that it is on a standard engine down to about 10.8 to 1. And the reason we did that was to try and keep the cylinder pressures down. You know, running that much boost, we didn't want to go blowing our cylinder block or blowing the cylinder head off the engine. So we did reduce that compression ratio. We actually had to preheat the engine by plugging a 5 kilowatt heater into the water circuit of the machine to get that coolant up to about 80 degrees C before it would even start. Of course, then you get the engine running, everything's nice and warm, but you want the air going into the engine to be nice and cool. So there's a few different methods we used to get that air nice and cold. So the first one was the WCAC, so the water charge air cooler. And what this does is it draws air once it's been through the turbo and compressed, and it's all fairly warm. You know, I think it was about 240 degrees C once it left that turbo compressor. And it passes it over a core of water to cool it down to about, I mean, we were getting WCAC out temperatures of about 10 degrees C. So, you know, in less than a second, that WCAC was getting that air from 240 degrees down to 10. So that's a lot of heat to take out of the air. And we looked at using just a water radiator like you would have on your car, for example. And some tractors have it as well. Our 8000 series has the same system, but we just could not get enough heat out of the air. So we ended up using an ice tank, so a water tank full of ice to try and cool that water flowing through the WCAC down with. So it was about 60 litre capacity. It would hold about 25 kilograms of ice, and we would use that ice in one run. So a run that lasted probably 70 seconds, we'd melt 25 kilograms of ice. And so we needed quite a lot of ice because we did quite a few runs when we were testing. I remember one time we had to send one of the engineers out to go and pick up or clear out the local Tesco full of ice because we had ran out. It was quite interesting. There's different ice has different characteristics. So, you know, different suppliers, their ice blocks are different shapes. So we did find that the Tesco ice was pretty good. It had a nice sort of cube shape and it had a nice sort of dome in the middle. So it kind of, yeah, it worked really well, the Tesco ice. So as well as the WCAC and the ice tank, we also injected water or a mist of water into the inlet manifold. And that really did help as well, control cylinder and also exhaust temperatures. So it's a system that quite a few high performance engines use as well. You know, 4 little nozzles spraying in this standard distilled water. There's a fine line. Too much water and you can cause problems. You can hydrolock your engine, but too little and stuff gets a bit too warm. We then had so the next step was cooling down the engine and also the oil within the engine, so the water and the oil. So we actually fitted big radiators in the side pods or the panniers of the vehicle. There just wasn't enough room at the front of the vehicle to fit them. So these relied purely on ram air, so there's no fans drawing air in. And that was just because at the speeds we were running at, the fans would have just created a restriction. And as I said before, we used a lot of the CFD to work out how to sculpt the bodywork so air could flow into those cooling packs on the side. And then another little thing we did was we 3D printed some piston cooling jets, so we used to call them the PCJs, and these it was unique to each cylinder, and they would splash oil on the underside of the pistons just to try and keep those cool as well. So we had quite a few elements to the cooling system. We did quite a few simulation runs to work out, well, how warm is stuff going to get? What kind of charge temperatures are we going to achieve? And a key thing was we simulated it over the duty cycle of the machine. So we didn't go for a steady state. It's got to cool at 150 miles per hour constantly. We said we know how long the run is. We know how much water, how much energy the water can absorb. We know what kind of ram effect we're getting from the air. So we can actually simulate that run really, really accurately. So just go on to the next slide. So this is just sort of an image of those different systems. You can see the charge air cooler at the top there. That was custom made by Denso, so that it could sculpt around the bonnet. The ice tank as well, which would sit at it sat inside the front bumper. So we could take some hatches off the front bumper, fill it with ice after each run. What else? We've got the water injection. It's actually around the other side of the engine, but that just consisted of, these 4 nozzles, a little tank, and a water pump. You can see the water radiator there on the side pod, and some of the bodywork and the inlet to try and draw air through it. So loads of cooling, but things still got quite warm. So this is a video, I'll start it playing in a second, of the engine at the test bed. So we actually tested this at Ricardo, but also at JCB Power Systems on our dynos there. So I'll just press go on this. Key things to look at here are really, the power and the torque, but also the temperature. And you can see the engine speed, when it gets to about 2000 RPM, so about now, the torque suddenly jumps up, and that's when the air pulse kicks in, the turbo kicks in, and we get that really big power surge. And now you can see the exhaust's getting really hot here. We're getting close to 1000 degrees C. It actually glows white. And this is the kind of temperatures that we saw actually on the vehicle as well. So not just in the test bed. We were actually blowing air over this to try and simulate the amount of airflow it would get when it was fitted to the vehicle. So yeah, it got really, really hot, and we thought, wow, we don't want things breaking when the machine's running. So we actually ended up 3D printing the exhaust manifold out of Inconel, which has got really good properties at high temperature. But also we 3D printed it because when you 3D print things, they tend to not try and move as much when they get hot, like a formed part would. And what we found is some of the bent exhaust runners were actually trying to straighten themselves out when they got to these temperatures, and the manifold was actually trying to tear itself apart. So yeah, the 3D printed manifold did the job and held up. So after all that, loads of engine testing. We actually fitted the engine to the tractor, did loads of testing, everything was going really well. And one day we went really fast, probably one of the fastest runs we had done. And we sort of went home and thought, oh, this is great. We've done really good. We were really chuffed. So on the Monday, we stripped the engine down just to check it over, took the exhaust manifold off, and I noticed one of the exhaust ports was a little bit wet. There was a bit of oil on there, a bit of fuel, and then closer inspection, some of the valves were bent. We thought, oh, this isn't right. So took the cylinder header off, and we actually found quite a melted piston. So that's the one you can see on your screens there. All the others were absolutely fine, in perfect condition. They looked brand new, but this one had got quite warm, and after a lot of head scratching and a lot of investigation, we found that the injector had actually got a little bit of swarf in it, which you can kind of see in that bottom picture. That had caused the needle to stick open, and that one piston was, that one injector was hosing fuel that, you know, it wasn't metered, it was going in at 2.7 litres a minute. So we made plenty of power that run, but we did blow a piston up. So full engine rebuild, new set of injectors, new set of pistons, and away we were going again. So I'm almost at the end. I've only got a couple more slides. So all that engine work created these curves you can see in front of you here. So 1,006 horsepower and 2,370 Newton meters of torque. And that was measured. We didn't measure that on the dyno because we only got to about 870 horsepower on the dyno and didn't want to do any more. We wanted to try and preserve the life of the engine. Things like running the cylinder pressures. I think we were about 210 bar cylinder pressure. The block was really being stressed, so we didn't want to run that block and that engine at the peak powers for too many minutes. We wanted to save that for the record run. So, I mean, this consisted of, we'd go out testing, we'd measure the speed, and then we'd slowly increase the fueling. We'd get the laptop, get the tractor back in the garage, plug the laptop in, change the map slightly, increase the fueling a bit, go out again, and just kept eking it up and up and up until we kind of got to the speed that we wanted to achieve. And yeah, it kind of came down to myself and my colleague to say, right, let's give it a little bit more fuel, guys. Let's try and get as much speed as we can. And we actually measured that 1,006 horsepower on the prop shaft of the vehicle. Richard Young's on the call. He's the main man at JCB Land Power about that, so we used a lot of his kit on there. So yeah, that was the final torque curve, and this is the final. This is actually the trace, the vehicle speed from the world record run. So you can see peak speed 153.771 miles per hour. So we achieved the Lord Bamford target, go faster than 150. And that resulted in the world record being set at 135.191 miles per hour. And looking at this graph, you can see that actually through that measured kilometre, the tractor was still accelerating. It still had plenty more to give, and we really were limited by the length of the runway. So, you know, longer runway, bit more room. I think we could definitely get a way faster world record run. I think we might be a little bit closer to that peak speed. So hopefully this is the video of one of the fastest runs. I don't think it was the actual run, but you can see Guy Martin driving it here. So you can kind of see the kind of acceleration we had. I think it was 0 to 60 in about half seconds. Here he's at Elvington. He's in 5th gear now, foot flat to the floor. We actually had 6 gears. We had another gear to use in the tractor, but we just didn't have the engine power. I think calculations said we probably need another 500 horsepower to be able to use that 6th gear, and then it would go pretty quick. But yeah, I think we get to what's this, about 150 miles per hour, and then slams on the brakes because the end of the runway does come pretty quick. We did use we used a standard braking system and standard suspension, standard steering off the tractor. And then there he is, comes in to turn around. We had an hour to turn him around, so put more ice in, refuel if we needed to, check everything over before he went again. And that was it. So I think that's the end. Yeah, that's it. So Simon, do you want to take over, see if there's any questions?
I think everybody's been mesmerised by the by your presentation, Alex. Thank you ever so. Thank you very much for your delivery there. It's brilliant. Because I don't see any questions on my chat. So has anybody got anything they want to quickly pen or
just unmute?
Okay, so we've got one coming in from Jim Loynes, and Jim said, what was the budget? So Jim, do you want to
if you can tell us, Alex, can you say how much you've actually spent on this? Was there a budget limitation set by Lord Bamford, or what was the situation?
Yeah, I mean, there's always a budget to these things. Otherwise, they can spiral out of control. I'd have to speak to the accountant to get the exact number. But it's always a tricky one trying to put a figure on how much sort of the benefits of it, all the different publicity, what the wonders it does for the brand. I think they sold loads of extra tractors because of it. So yeah, I don't know the exact figure, Jim, but I'd have to get back to you.
I'd imagine it'd be in several tens of thousands or more.
Yeah, probably. Yeah. It got the job done, didn't it?
Yeah, but I mean, presumably, you just said in there, the publicity and everything else about of doing it all has made JCB sell more fast track tractors. So fantastic. He's gone.
I think, Alex, we've lost your sound.
Oh dear, I've broken it.
Can you hear us, Alex? Could you perhaps repeat or try and cover the last bits that you mentioned, because we can't hear.
Oh. He's muted. Oh, I don't want that.
Alex, do you want to try going on mute and coming off again? You might just fix it that way. Now unmute. Devastating.
That's a shame.
All right, does that work now?
Yeah, it does. Yeah.
Yes.
Perfect.
Yeah.
Cool. Yeah, I don't know what happened then. I'll blame the computer network.
Or blame me.
Sorry. Yeah. So I think you had asked the question, Jim. Was there any others, Simon?
Yes, there's definitely is. Dave Clare asked the question about piston cooling. David, do you want to come and ask your question?
Yeah, you mentioned about putting some 3D printed jets or something to cool the pistons. How did you, and you said they're individual as well. How did you work out what pistons to cool and how to cool them individually?
Yeah, I mean, it was just, it was taking the CAD model of the engine, working out where the piston was at the bottom of its stroke, and then 3D printing the jet so that it would spray oil over the whole surface of that. So of course, you know, each one was printed at a slightly different angle, just to get it optimized really. So yeah, it was all done on CAD.
Okay. There's a question from Thomas. Thomas, do you want to come in and ask your question? If not, I'll ask the question. Basically, it asks what's the top speed you think could be achieved, and this then sort of links into the next question, which is Mark V says, do you think it would do 200 miles an hour? So
I think in its current state, it probably would do. This is a good question. Probably, if we had a long enough runway and we didn't alter the engine or the aerodynamics or anything, I think we'd probably get to about 160 miles an hour top speed. If we then decided, if we did some major changes to the engine, and increased that power to from 1006 to probably at least 1500, I think we could then get into sixth gear, and then we could actually we could go at least 200 miles an hour. But I think the ratio was, I think fifth gear was about 1 to 1, and then sixth gear is actually an overdrive gear. I think it was about 0.8. So you know, that extra ratio would give us plenty more speed, but you just need that power. You need that tractive effort to power through it. So yeah, longer runway, more power, and then yeah, she'd go quicker. And then we'd have to retest the tires because yeah, we only tested those to the speeds we achieved. So we'd have to make sure they don't get too warm and go bang.
yeah. Okay, Bill Basford, you had a question.
Yeah, I was really listening to what you said about where Lord Bamford reacted, etc. But where did the original germ of the idea come from? Was it the Channel 4, or was it the promotion team behind Guy, or where?
No, I think the story goes that it's something that JCB and I think the fast track team especially have always wanted to do. You know, that we sort of kept seeing these different world records happening, and we thought, well, you know, we can do better. We saw Valtra do it at about 80 something miles an hour, and then of course there was the Top Gear orange looking thing, which was basically just a pickup with a tractor bonnet on. So yeah, we really wanted to do it. So we kind of got the marketing teams involved and floated the idea past Lord Bamford. And then really, we then got the TV company involved and said, you know, would you like to do that? You know, would you like to televise this? And I think we had just done the that World War I tank program with Guy Martin. And they said, oh, well, yeah, you were really, you know, you were good to work with. We liked doing the tank program with you. So yeah, we'd like to do this tractor project with you as well. So yeah, I think everything sort of came together at the right time. And then, yeah, I was in the right place at the right time and got told to make it happen.
Yeah, good.
Okay. Question from Sam Scales. Is Sam there?
Yeah. Hello, are we there?
Hi.
Hello. Hi, yeah, sorry, it's Will Flitner and Sam Scales here. sharing a computer. It goes back to the gearing of the machine. I just wondered, why was it geared so high if the 6th gear wasn't really necessary, and why have it with the 6 gears, or why not gear it lower for better acceleration, or is it something for the future, or just how it worked out?
It's a good question. I mean, we were pretty much using the standard gear ratios of the gearbox. We did look at all different ratios we could have used, or altering the crown wheel and pinion, but we kind of, through the model, we kind of settled on, well, actually what we've got is pretty much optimized. The trouble I think we found, it was quite sensitive to the speed in which you changed gear as well. And we found that actually, if you factor in faster acceleration because you've got slightly lower gear ratios, but an extra gear change versus not completely optimized gear ratios, but one less gear change, it actually came out on top there. That, you know, 4 gear changes was enough. And I'm trying to remember the exact figure now, but it was like for every second the gear change took, it had, I can't remember the figure offhand now, but it was a certain percentage off that top speed. So the whole thing, it was quite a balancing act really, and having that simulation model really helped to sort of to quantify that and those decisions.
Thank you very much. That was fascinating. And what gearbox actually was it? Sorry if you've covered that already.
No, I didn't. I don't know if I actually said it was a ZF 6-speed. What was the name of it? An Eco. I think it was an Eco Max gearbox. So yeah, really simple thing, cable operated, synchro. We did look at using the CVT out of the 4220, and it would have done the job. It could have handled the torque, but it was just too heavy. I think that weighs 870 kilos versus our box, which was 200. You know, aluminium casing. So yeah, it was a bit of a lighter, simpler. We thought we'd just use that.
Thank you very much. Fascinating.
Okay.
Next question from Sarah.
Hello, thank you. Great talk. Thank you, Alex. Really interesting. So was this your 100% your work? Is this what you were able to dedicate yourself to? And how long did that take? And what was your highlight of the project, please?
Okay, thanks, Sarah. Yeah, I mean, I was lucky enough. Yeah, it started off as a part-time job, but then as the momentum got behind it, I was then able to move on to it full time, and that's, I mean, it started off with just me in a CAD box, working out, you know, where can I put the engine, where can I put the gearbox, how tall's the cab need to be, you know, doing all the initial calculations, and then I think when I told the bosses that yeah, it could be done, I then had to kind of put a bit of a plan together on how many people I thought I needed, how long it would take. So yeah, and then after that, yeah, the momentum got behind it. I got probably, yeah, there was 5 other engineers. As I said, they're all quite, you know, young, so we used loads of experience from the you know, the more experienced engineers. But yeah, so I think I worked on it for probably about 2 months on my own, and then once everyone got involved, it was probably 9.5 months working time. So yeah, it was really good. And highlight, well, obviously the day where we broke the record and we sort of pushed the engine to its absolute limits. You know, we'd only ever tested it to 866 horsepower on the dyno. So yeah, it was quite exciting, just, you know, nudging that fueling up on that engine map and seeing what we could get out of it. So that was really good. But I think apart from that, the other thing is probably just that first fire up, you know, once after all that hard work, just getting the engine into the machine, starting it up for the first time, and then just seeing it zoom down the runway. It was pretty cool. Okay.
Okay, the next question from Adam. Now, Adam's got, apparently his microphone's not working, so he's asked me to ask the question for him. He says, brilliant presentation, Alex. Yep, thank you. Is there any of the performance upgrades that you used for this that indirectly you found could be utilized for general production? So any sort of trickle down into general production, I suppose.
Yeah, it's a really good question. Yeah, I mean, obviously just looking at the engine to begin with. So we have looked at these electric superchargers and done a bit more investigation into how they could be used, and it's all about, especially for our machines, boosting that transient response. So how do they react when, in your tractor you come across a hard patch of ground and you need that instant power boost, or on a digger when it digs into a pile of ground. So there has been work done looking at these electric superchargers, and perhaps they'll be part of engines of the future. At the moment it always comes down, especially in our industry, down to cost. So they're not cheap. You need a minimum of 24 volts, 48's better. So then you need batteries. We used lithium-ion batteries, which again are quite expensive. So they've got loads of benefits, but the downside of them is the cost. So that's a key thing on the engine. Tractor wise, I think just the whole efficiency side of it and weight saving. You need weight sometimes, but then again, sometimes you don't need the weight. Minimizing that, when you're on the road, that always helps. And also things like rolling resistance, and just looking at new tire technology. Is there any ways that we can just reduce that, and working with the suppliers, because especially our tractors, they spend a lot of time on the road, and fuel's not getting any cheaper. So yeah, there's a good bit of learning from this. So I think, yeah, that's it. Is there any other ones, Simon?
Yeah, yes. Charlie, can I invite you to present your question?
Yeah, absolutely brilliant presentation, Alex. Really interesting. I've seen a tractor, a fast track, roll at about 35, 40 mile an hour on a bend on test, and it's not a pretty sight. So my question really was, you got quite a precious cargo on board. What consideration was done to protect Guy if there was an accident and something did go wrong, like he blew a tire up and lost control?
Yeah, really good question, Charlie. Thanks. And yeah, to be honest, I didn't cover. I mentioned about safety at the beginning, but I didn't actually go into the details of what we did. So, I mean, the key.
We've lost.
No, you've been muted again. Lost your sound, Alex.
Lost the speaker as well, I think.
Oh dear. He's wondering why we're pulling faces at him.
Faces at him now, yes.
He's probably giving a really good answer as well.
Yeah. Go on, shout.
Yeah, probably cased him in Kevlar or something, just in case the engine blew up.
They actually took some technology from the truck racing guys, or
I
tried
know.
to, but then they realized that the truck racing guys didn't do 150 mile an hour.
No,
I know they had a proper race seat in there and harnesses, roll cage. I think it was a proper FIA roll cage in there as well.
Yeah, because when Alex said that the cab was narrowed and that, then obviously it just became a box to sit in. It obviously hadn't got any stiffication from that point of view. So obviously,
No, I think it had a pretty substantial roll frame.
Additional,
it was a tubular roll frame.
Tubular
I
frame
think they had like the race people look at it, if I remember. I remember talking to one of the guys about it. At the time.
that's good. Oh, that's Sage. Well done.
That's a hell of an answer he's giving, isn't it?
We're still...
Alex!
We can't hear you, Alex.
You can't hear us, obviously, as well.
No, he's lost.
Oh, no. Oh, dear.
Can't you do anything, Mr. Chairman? Can you press any more buttons?
I don't know who he's got up on his screen. If he's still got his presentation up, he won't see.
Well, we put messages on chat.
Yeah.
A few of us are waving at him. That's all we can really do. Wait until he stops his talking. He might notice something.
Simon, do you want to give a wave? Yeah, the joys of technology, eh?
Yeah, he's still.
Yeah, I don't think there's anything like as Hurst that can do to actually attract his attention.
No, I mean, he's probably had loads of messages saying they can't hear him.
Mm-hmm.
We assume that the problem is at Alex's end within either within his hardware or the system.
I think
Does it work now?
Yes. Alex, you've been off for about 5 minutes.
Can you hear me now?
It looked a bloody good answer you were giving, Alex. Anyway, we didn't hear any of it.
Does that work?
Yes.
Yeah, working now.
Can you hear me now?
Yeah.
Yeah.
Right. Yeah.
Yes.
Oh, you can hear me. Is that Simon as host? Can you confirm? Is that good?
Yeah.
Yeah.
Okay, so you can hear me.
Indeed.
How much did you not hear? Probably
all of it.
Basically all of it, yeah.
Hang on, because I can't hear you now. So let me just try and reset that. Yeah. Okay. Right.
Can you hear us?
Okay. Is that better?
We can hear you.
Hey. I don't know what's happening. My computer just automatically mutes me and then mutes my speakers as well.
Yeah, so we missed the whole of your answer, Alex.
Oh no. Okay, well, I'll start again.
Well, probably quickly, but from chat specifically on the cab and looking after Guy.
So I talked about to myself then DFMEA, so designing safety in right from the beginning.
Yeah.
Things like steer hoses, making sure they're routed correctly, so they're not going to rub on something or get damaged. And then I talked about, what did I talk about next? DFMEAs, and then doing loads of rig testing, like on the tyres, working out all the limits of all the components, and then fitting all the different sensors to the machine, so that if something was going to go wrong, we could try and predict that it was going to go wrong and tell the driver. And the way we did that was had a big red light that would flash on the dashboard saying stop, something's wrong with the tractor. And then if those two steps hadn't worked and something was going to go wrong, we put a huge roll cage into the machine. And this was certified by the FIA. They didn't actually have a category that was suitable or a, one that they had done in the past for a vehicle like this. So we actually used their off-road truck category, which was sort of the closest thing we could find. So again, with that, we did loads of FEA analysis on it, inputted all the different load cases. We then submitted that to the FIA so they could analyze it and also do their own FEA analysis on it. They came and observed the construction of the roll cage and the installation and made sure it was all correct. And then we got an FIA sort of data plate that we could actually stamp onto the roll cage to say that it was approved. So yeah, quite a few different levels of safety really, but it had to be right. It was our primary concern really throughout the whole thing, keeping the driver safe.
Yeah.
Excellent, thank you.
Okay.
Okay, Dave, you had a question?
Yes, maybe a bit of a controversial question. I don't like this one. Many years ago, county tractors used to be very, very good in wet conditions, and they'd cross the channel with a modified tractor, and at the end of it, they came on land in the UK and then went and ploughed a field, just to prove it was a real tractor.
Yeah.
So, do you think this is what you produce as a real tractor, or just a fast machine that looks like a tractor?
Yeah, no, that's good. You're definitely not the first person to say it. So it was always part of the project, and right from the beginning, it had to be able to do an agricultural task, and that's what we designed in right from the very start. So it could go out and disc a field if we wanted it to, and it's something that was going to be part of the TV show, and there was lots of toing and froing as to whether they were going to include it or whether they actually wanted us to do it. But yeah, it's got a fast track axle on the back, so it's got the fast track suspension links, cylinders, steering, so everything is capable of towing something. Okay, it didn't have a 3-point linkage fitted, but we could have quite easily bolted one onto the back of the axle and lifted something up. Yeah, we'd have to provide hydraulic power to it, but it's all doable. We couldn't have just finished the record and straight away gone into a field and ploughed. We would have obviously had to fit the tow hitch to it, but yeah, it could have done the job. But I think it was just decided that it didn't need to, because the Diesel Max car, for example, after they did the run, they didn't decide to go out and drive down the road with it. I think that was the kind of rationale behind it. But yeah, I would have quite liked to see it being done, and it could. So who knows, in the future we might be able to dust it off and do something with it.
It'd be good to see it working. Yeah, thank you for the presentation. Some great engineering there.
Thanks. Yeah. It was. We learned a lot throughout it, myself and the team.
Okay, there's quite a few comments relating to when we had our transmission interruption, shall we call it?
Sam, could I just
yeah,
ask a question? Alex, I mean, you know, I had the privilege of seeing this thing in build. And I mean, the quality of engineering and just, you know, you had an excellent presentation tonight. And I think clearly the cutting edge nature of pretty well every system on the machine has come through. How have you found it? And the other team members now going back to the real world, if you like, of JCB? Because I mean, you're on this high, the spotlights are on you, the TV cameras are on you, and then all of a sudden you're back into roaster on Monday morning.
Yeah, I mean, obviously, yeah, it was absolutely amazing to be part of, and I think we're all really lucky. But you know, I think the fact that we've all gone back to still doing a pretty similar job, we're still designing machines. You know, they're not quite doing the same thing, the same duty cycle, but you know, we're still on CAD, we're still doing all the sums, all the simulations, and actually, you know, when we were doing the project, and when you're in that, you know, that nitty gritty and all that detail, you know, it could have been anything we were designing. You know, we had that goal of this is what it needs to do. But when you're looking at, I don't know, tolerances on, you know, the tolerance stack up on an input shaft for the world's fastest tractor gearbox, it could be the input shaft to anything, you know, any JCB machine. So I think what I'm trying to say is the engineering behind it, we're all still doing today. So I think it helps that we've got pretty cool and pretty interesting jobs. I think if we had gone back to just being, you know, accountants or whatever, it might not be quite as fun. But I think, yeah, we've got a fun job.
Good answer. Good answer.
I suppose carrying on from that, Kit Franklin had a question. He said, basically, how did you find working with the film crew? Was that?
Oh yeah. I mean, it was all right. It was a bit weird at first. You know, I've never really liked doing that sort of thing. But I think they were quite good in the way that they film their stuff for Guy Martin, where they pretty much just have cameras running all the time, and none of it's really staged or sort of scripted. They don't do loads of retakes of stuff. You kind of just have a chat and get on with it when Guy's there, and then they kind of cut it and paste it into a TV show. So it was pretty relaxed, really. I think the worst bit was when they you know, like after we did the record run, they do these things called post-match interviews, where they basically sit you down and then like ask you a load of questions, and you don't really know what they're going to ask and what quite they're going to actually put into the TV show. So that was the only daunting bit of it. But they were fine. They're really friendly, and Guy Martin's just the same in real life as he is on the TV, really. Pretty enthusiastic and really interested in everything, and you know, really interested in a lot of the detail. So yeah, it was good.
Alex, I guess, sorry, it's me. From my point of view, it's kind of from a project management point of view, I have had the misfortune of having to deal with film crews relatively regularly over the last few years. And I know that they have a tendency to change their mind all the time in terms of when they're coming and what they're coming to see. So it was, I'm pretty sure once they're there, they tend to be fine. It tends to be the months and weeks leading up to it that they're a right pain. That was from a project management point of view. Were they pain or not?
No, I mean, they were pretty good, to be fair. You know, we knew quite well in advance when they were coming, or you know, what they wanted to achieve when they came. So it's kind of just planning around it and really just building it into the plan from the beginning. So yeah, they were pretty good. If they said they were going to do something or they were going to come on a certain day, they generally would. So yeah, Channel 4, they were all right, really.
There's a couple of questions I've just seen come through, Alex. One of the questions is from Sedge. Did they strip the engines after the runs?
Not after every run. We only stripped the engine because we found that problem with the melted piston, and we only found the problem with the melted piston because we were quite interested in the exhaust manifold at the time and how it was it was trying to tear itself apart, and we were getting instances where you could see it wasn't quite getting to the stage where it was tearing, but you could see it trying to sort of, you could almost see the tear marks. So we thought, all right, well, we'll take this manifold off and we'll try our 3D printed one next. And yeah, when we took it off, we saw these wet exhaust ports and thought, oh, that's not great. So yeah, and then saw bits of piston coming out. So we thought, yeah, we better strip this one down. But apart from that, we would, after each testing run or testing session, which they normally lasted 2 or 3 days, and we'd be testing quite a lot. We'd be doing, I don't know, 8 or 10 hour days testing, and we probably did 5 or 6 of those sessions. We would then do an oil analysis test. So we'd take a sample of oil or a couple, and we'd send those off to the lab to get analysed, and that tells you a lot. That tells you if there's bits of metal floating around or too much fuel. You can make some pretty good decisions and conclusions from that analysis without having to strip everything down.
Another question again from Sedge. Have you written like a lessons learned about the project?
Yeah, I guess I have. I mean, I'm on a different project now, and there's lots of things from that where, from this one that I'm sort of I'm applying. But yeah, not necessarily sort of written down and sort of shared with people, but just sort of there's a lot to learn about, leading people and getting stuff done. I think I'm trying to put some specifics to it, but I think it's just that, getting your head down and just getting on with it, and a lot of that comes down to knowing having a really clear goal right from the beginning, and that's what we had. We knew exactly what we needed to achieve, and there was no scope creep and stuff changing here, there, and everywhere. We kind of knew what we had to get done, and we could all just be really efficient and just get it done. So yeah, I guess maybe that's a good one to sort of draw from it, is have a really good, clear set of objectives right from the start, and get everyone focused on those.
You also learn from Harper Adams then, because that's what we keep telling you, isn't it? When you're a student.
Yeah.
Specify things and don't let your mission creep.
Yes, yeah, well, that's it. And yeah, because it takes a lot of time having to design stuff and test stuff 2 or 3 times.
Very good. Fantastic.
Good.
Well, I can't see any more questions. Can you, Simon?
There's just one come up from Will and Sam, or whoever's piloting the laptop there. So Will Flickner.
Go on, ask the question, Simon.
Hello again.
Hello.
Sorry, another gear ratio question, because I've clearly got this fixated in my mind tonight. But I was just wondering, we've talked about daft ideas of dragging a plough or a set of discs behind the machine. Would it actually work slow enough in theory with the gear ratios and stuff and all the modifications you've done, or not?
Yeah, and I'm trying to remember the speed now. It's been a year since I've thought about any of this. Because basically we didn't use first gear in the gearbox. We set off in second gear, and that's because first gear was quite slow. I think it was like, what was it? It was about when first gear was fully engaged. I think it was around 8 kilometers per hour, something like that. So it's not like crawling field speed, but you could probably quite comfortably pull a set of discs or whatever. And because we had this JCB clutch, you can actually slip it for quite a while before it gets too warm. So yeah, it could do something.
Thank you. You just settled a good debate in the student house. Thanks for that. Very much.
Jim, final question from you.
I was going to say, how did Sir Anthony receive all the news and everything else? Was he very pleased with you guys, giving you a pay rise and Christmas present?
No, we got these T-shirts that say "World's Fastest Tractor" on. No, yeah, I obviously was really happy. You know, said thanks for all the hard work, and yeah, you know, I think it was really good. And then as someone said before, it doesn't take long to then get thrust into doing a different project and head down and you just get on with that one. And so it's been quite nice, really. This just revisiting all the stuff and writing this presentation. It's been good to remember it all, really.
Yeah, well done.
Good.
Cool. Well, yeah, I mean, if anyone's got any other questions they think of, just send me an email, alex.skittery@jcb.com, and I'll do my best to answer them. And then, you're quite welcome to come and look at it one day when COVID allows, when Boris says we can all move around again.
Yeah. Okay, so I think with that, we'll perhaps call proceedings to a halt for the meeting. Alex, thank you ever so much. Thank you very much for an excellent presentation. We'll do a sort of virtual sort of round of applause or whatever you do in this situation.
Excellent presentation.
And
Top job, Alex. Well done.
Thank you.
That's very good.
Excellent.
And thank you very much.